The name of this video is Inductance. In fact, I'm going to briefly review the main concepts of inductance as we have seen them during FES 242. Eventually, in 342, we are going to delve into more details about inductance, as we shall see in a few videos from now. So, what is the definition of inductance? In order to understand it, let us sketch the usual skiing hat. So, the hat we use when we go to ski. And so, this is a sketch of a line that is a border, a contour if you want, and is oriented, and we call it gamma. Let's orient it in this fashion. This is our gamma. One possible surface which has gamma as a border is the surface right here on the board itself. And this surface, we call it, let's say, capital sigma gamma prime. Another possible surface is the hat itself. So it could look something like that. And this surface here, we call it capital sigma gamma double prime. In fact, there is an infinite set of such surfaces which share gamma as a border. This is just two of them. Suppose I want to compute the flux due to a magnetostatic field B existing in this region of space. How do we compute such a flux? Well, by definition, we know that the flux through an open surface, capital sigma gamma, where capital sigma gamma represents one of any of these infinite set of gamma prime, gamma double prime surfaces of B dot NdA. However, we know that B is solenoidal, and so we can rewrite B as the curl of A. Therefore, this integral simply becomes the surface integral on a capital sigma gamma of the curl of A dot NdA. So this is the flux through any surface capital sigma gamma. All right, so now we can use Stokes' theorem, which eventually gives us, from Stokes' theorem, TH for theorem, we obtain simply the line integral along the closed line gamma oriented in this fashion of A dot TdL. So this beautiful and simple proof, which is based on the usage of Stokes' theorem the other way around from what we typically do, tells us that the flux through any of the infinite set of surfaces capital sigma gamma type which have gamma as a border actually is independent of any of those surfaces, depends only on the border which those surfaces share. So it's just the line integral, the circulation, in fact, of A dot TdL. This is a very important concept. It's actually beautiful. In the end, we only need to know gamma. That's all we need to calculate the flux and the vector potential A. We will come back to this extensively in 342. In fact, we are going to use this concept in so-called Neumann integrals. So Neumann integrals is a very general approach to study the inductance, mutual and self-inductance of circuits and devices in general. And in particular, we are going to use it to show the so-called Maxwell's inductance, which is really a thrilling topic. In fact, you can Google for the inductance of a loop, of a simple circuit loop, a filiform loop with a current. They will tell you the result for that inductance, but it's very hard to find the proof of that inductance, which is due to Maxwell. And so we are going to find out, I'm going to show you that proof, which is really a very elegant example of how to use approximation in physics, which eventually lead to the inductance of a loop, which seems very innocent, but is not. Great, so we will come back to this extensively in the next few videos in 342. So now to summarize this concept of inductance, now that we know that the flux is independent from the surface itself, what we want to do is to remind ourselves of this concept of inductance, which I know is always a problem with most students. We have seen very similar concepts when we discussed about capacitance and resistance. They are exactly the same kind of concept, but for some reasons, when it comes to inductance, it seems more complicated. So, Let us consider, for simplicity, a single quasi-filiform or filiform conducting circuit, so a wire. Let's sketch it down here. So let's say that this is our wire. This wire is oriented, and we call it gamma 1. And it carries a current I1, which let's say is a steady current. Typically, when we do experiments and we want to test inductance, we can use any current, but for simplicity, we can use a steady current. So let's suppose that the steady current goes in this direction. This is I1. If the direction of the current is equivalent to the direction we have chosen for gamma 1, which is just a geometrical representation of the circuit, then in this case, the current has a positive sign. So it's positive. If we had chosen the orientation of gamma 1 to go to the opposite of this orientation, then I1 in that case, it would be a negative. So in this case, suppose that, of course, in order to establish a steady current I, we need to make use of an EMF, an electromotive force, E. And suppose that we change during the experiment this battery, the electromotive force, in such a way that eventually we get a current I1 prime, which is linearly proportional by means of a coefficient K, which depends on my EMF, to I1, the original current we have chosen in the beginning of the experiment. For example, I can linearly increase this current, okay, on the circuit by increasing the voltage on my battery. But suppose that I do that, since everything is linear in this circuit, in fact, all these discussions are only true for linear scenarios. If we were to introduce here a ferromagnet, like the magnet you put on your fridge, then things would change. We will study ferromagnets later on in 342. Now everything is linear, so assuming that everything is linear, then, and if it's not linear, you need to linearize it somehow by means of a Taylor expansion. We will briefly discuss about this later on in 342. Well, also the flux through gamma 1 prime, due to the current I1 prime, will be proportional to that due to the original current without prime, I1. Now, clearly from this equation, here we can see that K, from this equation here, is nothing but I1 prime divided by I1. Is this simple proportionality constant. Therefore, we can rewrite this quantity here, substituting K here, as phi gamma 1 divided by I1, which is the current generating that flux, times phi times I1 prime, which is in the numerator. So I1 prime divided by 1, and I put this together in this fashion. This quantity here, in parentheses, is what, by definition, we call the self-inductance L1 associated with this circuit. So the self-inductance is a fundamental property of linear circuits, which tells us that the flux divided by the current that generates that flux is always a constant value, regardless of the amplitude of the current that generates that flux. It's always constant. So phi over I is constant. I increase I, phi increases proportionally in such a way that the ratio is always a constant. This constant is the self-inductance of this object. It's an empirical evidence. You do experiments, and that's what it comes out. Now again, as I already said in 242, it seems that people have lots of problems in understanding this. It's just a proportionality constant. Do you have a problem when we say that the force is proportional to the acceleration by means of the mass, F equal ma, in the first Newton law? No, this seems we accept it because it's given to us, it's kind of, that's what it is. And here is the same thing. So if you don't question the role of mass, which is also a proportionality constant if you want, why would you question the role of inductance? You do experiments and it turns out this is what comes out. Now in the case of capacitance, you can even more formally, you can do it also here. But for example, in the case of capacitance, it's exactly the same concept. The capacitance is the constant ratio between the charge and the potential difference on a circuit. Now, as it turns out, that's also a property of harmonic functions. So you can very elegantly and simply, already with the knowledge you have, prove it mathematically. But that's what it is. It's just an empirical evidence. Now, more in general, suppose that I consider another circuit here. This circuit, let's call it gamma 2 oriented in this fashion. Now, in general, this could also carry a current, I2, and for example, for generality, let's choose that this I2 has a negative sign. It goes in the opposite direction compared to the orientation of gamma 2. So in this case, forget about it, there is this script in between, of course, they're just two coupled circuits. Now, if these two circuits are coupled, some of the B field line generated by I1 will eventually be coupled also to the lines, this is B1, to gamma 2. So this linkage here results in a so-called mutual inductance, and so the flux on the second circuit 2 due to the first circuit phi to 1 is given by the mutual inductance M, which has the same units to 1 of the self-inductance, times the current I1. And the units of all these quantities are capital H, which means Henry. And when you write it in full, you just don't capitalize in SI units the first letter. So it's just Henry like that. All right. So we will come back to this concept, and eventually we're going to write down a system which relates the flux on the first and second circuit by means of their self-inductances and mutual inductances. As it turns out, the self-inductance is always a positive quantity. So L must be positive. Always. Whereas the mutual inductance can be negative. Can be both. All right. So in order to fix the ideas here a little bit, let us consider a very simple example, which we've done already in, is a simpler version of what we've done already in 242, and it was actually the very last question of the take-home exam in 242. And so let's separate these into two boards. So the the coupled circuits I want to consider are an infinite straight line of current, so carrying a steady current I1. So let's catch it here in this fashion. So this line carries a current I1. This is my line, oriented line, gamma 1 if you want, which is infinitely long in this case, therefore these dashed lines. We then consider somewhere on this board here on the right hand side a rectangular filiform circuit. This is also filiform. Which we call gamma 2, and we orient in this fashion. In order to find the mutual inductance, we set to 0, as we have seen in 242, the current I2 on this circuit. So this is just a circuit with this orientation, gamma 2. Dimensions, in order to understand dimensions, is worth choosing. We could choose a Cartesian coordinate system, but it's better to choose a cylindrical because we have an infinite straight line. So this is the r-axis of a cylindrical coordinate system, r. This is the origin, O. This one is the z-axis of this system, z. Right-hand rule, phi goes into the board in this fashion. So this is bar phi, okay? In this specific case here, it's worth noting that since right-hand rule, gamma 2 is oriented towards me, so obviously the n2 normal unit vector with respect to this surface is equal to minus u bar phi, is the opposite of the bar phi unit vector. Dimensions, this is capital R1, this is capital R2 on the r-axis, R2 is larger than R1. This quantity we call it Z naught, and this quantity we call it Z naught plus a height h. So now we need, in order to solve this problem, in fact, with respect to this cylindrical coordinate system, what we intend to do, we intend to calculate the flux through gamma 2 due to B1, which is the field generated by the magnetostatic field generated by I1. So we want to compute the flux through the surface associated with gamma 2 of B1 dotted M2 dA. With respect to this coordinate system, this flux simply becomes the integral between z naught and z naught plus h in dz, this is part of the dA, integral between capital R1 and capital R2. Even though we are in a cylindrical coordinate system, this is a rectangle where R and Z are effectively Cartesian coordinates, equivalent to Cartesian coordinates if you want, so it's just the area of a rectangle, so don't get confused by sine of theta or things like this. Here we just have a dr, so dr dz is the area of an infinitesimal quantity here on this surface on the board, which for example could be one loop of a toroidal solenoid, as we have seen in 242, but this is just one loop, okay? It's not a toroidal solenoid, so keep in mind that. So times dr, okay, and this one, we now want to compute b1 dot n2. But what is b1? b1 is some constants, which we know are mu naught times I1 divided by 2 pi, 1 over r, and then here we need to compute the directions associated with this product, dot product, will be right-hand rule. I1 points up, so B1 points as u bar phi, dotted N2, which is minus u bar phi. So we pick up a minus sign from this dot product. So we have a minus sign in front of all this quantity here. And finally, so here we are doing N2, we put it, and here we put it, B1 has all the units, perfect. So we end up having minus, the flux is minus, so it's negative, mu naught I1 divided by 2 pi. This integral gives us a height h, whereas this integral is the integral of 1 over r, so it's the natural logarithm of r2 divided by r1. By definition of inductance, we know that this quantity has to be equal, this is the flux through gamma 2, and so it's the flux on 2 due to 1, so it has to be the mutual inductance between 2 and 1 due to the current I1, and so finally the mutual inductance M to 1, so again this is nothing but phi to 1 in this definition up here, down here. So M to 1 I just need to divide by I1, so I divide by I1 and I obtain it is a minus mu naught h, we got rid of I1, divided by 2 pi, natural logarithm of capital R2 divided by capital R1, which interestingly enough is a negative quantity. Mutual inductance can be negative. What happens, question for Piazza, what happens, what if gamma 2 was oriented the other way around? In this fashion. What would be the case for M to 1 in that scenario? So to summarize this video, I wanted to give you a refresher about inductance, which we've seen in 242. So the first thing which I wanted to stress is that the flux due to a magnetostatic field B is independent from the surface. It only depends on the border that an infinite set of surfaces share. And therefore it can be calculated as the line integral, the circulation of the vector potential .TDL. We will use this in normal integrals. Then I introduced the concept of self-inductance, which is the ratio between flux and current. N is universally a constant, which call it the self-inductance units of Henry. We then introduced this concept of mutual inductance, which is connecting two circuits because there can be a linkage of the magnetic field due to the first circuit on the second. Mutual inductance can be negative. To fix ideas, we look at the case of an infinite straight line of current and calculated the mutual inductance on a filiform conductor in the shape of a rectangle, in this case here, and we found that it's negative, and this is the well-known result, which is the natural logarithm of R2 over R1. Now, if this was one loop of a toroidal solenoid, you would also need to multiply times all the loop to find the overall mutual inductance, so it would be an n being the number of loops, as we've seen in 242. That's it.